So we've been talking here at the end there about empirical formulas. And again, a reminder that empirical formulas really are, as we talked about, the simplest whole number ratio, what is present. It doesn't necessarily always tell you exactly what is present in a particular compound, but it does give you that simple ratio of what elements there are in it. As I also mentioned, there are some formulas which both the empirical formula and the molecular formula are really the same. And that's because, again, they are in sort of the simplest ratio that you could get. So a couple other examples of some covalent molecules that are like that. NH3, which obviously has basically one nitrogen for every 3 hydrogens. That is really as simplest as you could get it, along with our carbon dioxide here, 1 carbon and 2 oxygens present, the simplest ratio. As I mentioned before, all ionic compounds, their formulas are really empirical formulas. So if you think of something like calcium fluoride, right, we put it together in the simplest way to get to 0. Sodium chloride, whatever it may be, potassium nitride. Those are all really empirical formulas when you do have an ionic compound, and obviously the simplest ratio there to get you to 0. So let's take a look at a few examples here, take a minute or two and figure out what is the empirical formula for each of these molecular formulas and see what you come up with. Okay, so again, remember that the empirical formula really is the simplest whole number ratio, what's present. So if we look at the first one, we really have 2 carbons for every 2 hydrogens. You could definitely reduce basically everybody down by 2. And that basically would give you 1 carbon and 1 hydrogen as our empirical formula there. Any question on that one? Here we have I2O5. That is basically 2 iodines for every 5 oxygens that are present. In this particular case, that's pretty much as far down as you can go. You cannot reduce it down anyway to still get whole numbers. So actually the molecular formula here and the empirical formula would be the same in this particular case. And lastly, we got glucose there. We got like 6 carbons for 12 hydrogens for 6 oxygens. We clearly could go around and take everybody down by 6 or divide by 6. That would give us 1 carbon, 2 hydrogens, and 1 oxygen as our empirical formula. Any questions on how to get there? So in a case where you are given the empirical molecular formula and you want to calculate the empirical formula, pretty much the simplest way to do it is just to see if you can reduce everybody down by a common number to obviously still achieve you whole numbers. If you can't like the middle one, then that would obviously be both the empirical formula and the molecular formula. Another important thing that's oftentimes used with empirical formulas and molecular formulas and sort of calculating those two are what are referred to as percent composition by mass. It's very similar to sort of the calculation with the water that we sort of talked about the other day there with the hydrate. But basically, we could get the percent composition by mass of each of the elements that are present within a compound by basically taking the mass of each element that's there and dividing by the molar mass of the entire compound. So kind of similar to the other day where we had I don't remember what it was. I think it was maybe this one. Yeah. And you wanted basically the percent of water present, sort of theoretically. We could take the mass, the molar mass of the 7 waters, as we talked about, divided by the molar mass of the hydrate, and obviously times it by 100%. And that would give us our percentage of water that was present. In this case, we can do it from a formula and take each of the individual elements that are present and calculate the percentage by, again, just taking the percent of the element would be the molar mass of the element divided by the molar mass of the compound times 100%. So if we take a look at one here, like hydrogen peroxide, the first thing that we would want to do is calculate the molar mass of hydrogen peroxide. So the molar mass of hydrogen peroxide, like we were talking about earlier, There are 2 hydrogens from the periodic table, 1.008 for each hydrogen, plus 2 times 16, which is the molar mass from the periodic table for oxygen. That would give us a molar mass for hydrogen peroxide of looks like 3402 grams per mole. So if we wanted the percentage of hydrogen here, it would be 2 times 1.008 divided by the molar mass of the entire compound times 100%. And if we do that, we end up with times by 100 would be good. There we go. We end up with, it looks like 5.926% hydrogen. And obviously we could calculate the percent of oxygen the same way. In this case, it would be 2 times 16 grams per mole divided by 3402 grams per mole times 100%. And that gets us, call it 94.06% oxygen. By the way, when I'm all done, these percentages should add up to 100% and approximately, again, won't be perfect, but should add up to about 100%. We got about 99.9%, pretty close here in this particular case. That also means that technically speaking, after we calculated the percent of hydrogen, because these were the only 2 elements in the entire compound, we could have just subtracted 100, right? 100 minus that, and that would have gave us obviously the other number. So you could obviously do that when you're down to sort of your last element if you want in a formula. Any question on that calculation there? Now the question is, would it come out any different if we actually use the empirical formula versus the molecular formula for hydrogen peroxide? So if we look at the empirical formula for hydrogen peroxide, which is HO, we could do a similar calculation and we would get the molar mass of HO, which would be 1.008 plus 16 gives us 1701 grams per mole. Then calculating our percentage of hydrogen in this case would be 1.008 divided by 1701 times 100%. Come here. I can throw my calculator out in a second. Here we go. Come on. There we go. Gets us 5.926% hydrogen. And obviously doing our same guy here for oxygen. Gets us 94.06% oxygen. So is the percent composition by mass different for the empirical formula versus the molecular formula? And just in case you don't remember, what do we got there? We had 94.06 and 5.926. So they are the same, and that's because, again, the empirical formula is really the simplest representation of the elements that are present, which means by mass, you're going to have the same percentage of each of the elements that are present. If you did percent composition by mass for the molecular formula or the empirical formula. Any questions on that one there? Okay, so why don't you try one here? What is the percent composition of hydrogen, phosphorus, and oxygen in phosphoric acid? Hydrogen is 1.008. Phosphorus is 3097. and oxygen is 16. All right, so see what you come up with. We want to basically get the molar mass of the entire thing. So we got 3 times 1.008 plus 3097 for our phosphorus, plus 4 times 16 for our oxygen, giving us about a 97.99 grams per mole. To find our percentage of hydrogen, we would take 3 times the hydrogen mass there, divided by 97.99, times it by 100%, and 0.008 divided by 97.99 times 100 gets us a 3.086% hydrogen. We could then do it for phosphorus, which would be 3097 since there's just one there, divided by the mass of the entire thing times 100% gives us 3097 divided by 97.99 times 100% gets us about 31.61% phosphorus. At this point, again, you can just do the calculation, which would be 4 times 16, 799 times 100%. Gets us about 65.31% oxygen. The other option obviously would be like we just talked about. You could have added the hydrogen and phosphorus together and then took obviously 100 and subtracted it at that point as well. Any questions on how to calculate percent composition by mass? Yeah.
I got the right answer, but it shows the grams per mole in the calculation. That'd still be right.
You do need to show this calculation. At minimum, you should at least put grams on there. Yeah. Okay. Other questions? Okay. So what we're going to talk about next is actually how to calculate an empirical formula, and percent composition is used a lot to do that. So let's talk about the steps to calculate an empirical formula. Obviously, when you are not given the molecular formula. So very, very commonly, what you are given is what we just calculated there. Very commonly, you're given the percent composition by mass. So very common in empirical formula problems, you're given, hey, there's 50% carbon, 20% hydrogen, and so forth. So the first thing that you typically want to do when you're given that information is just to convert your percentage into grams. The easiest way to sort of turn a percentage into like a usable number is to assume you have how much? Yeah, you assume, for example, you have 100 grams. That means obviously if you have 50% carbon, you would have 50 grams of carbon, right? And it kind of keeps obviously the percent numbers the same. Once you have everybody in terms of the elements in grams, the next thing you want to do is convert grams to moles. And obviously, as we talked about earlier today, that is going to be your molar mass that you're going to use to do that. That grams per mole that we get from the periodic table would be what you would want to use to convert from grams to moles. At this point, you will have the moles of every element that are present. So you'll have the moles of all the elements. So what you want to do is divide by the smallest number of moles. So for example, if I had 2 moles of A and 4 moles of B at this point, just for an example, what I would want to do is divide everybody here by 2, since that is the smallest. And when I would divide everybody by 2 in this case, that would give me basically 1 mole for A, and that would give me 2 moles for B. And if you do this at this point and you divide by the smallest number of moles and you get all whole numbers like I just did there, that would technically be your empirical formula. So my empirical formula in my example here would be AB2. Any questions on that there? Now, if I divided, let's just say I had a different example here. Let's say I had, let's go with 2 moles of A and 5 moles of B. When I divide by 2 now, right, I end up with 1 mole of A, and 5 divided by 2 is 2.5, I hope, moles of B, which technically would give me an empirical formula of A, B 2.5. Can I have like 2.5 of B? I cannot, right? They do need to be the simplest whole numbers, right? So this sometimes happens when you divide by the smallest number of moles, you actually don't hit a whole number. So in this case, what we typically want to do is, this is considered a little too far to round. So, you know, if you end up with something like 0.5, 0.33, something like that, you know, 0.25, something of that nature, those are kind of considered too far to round. If you divide and you end up with something like 0.999, obviously that's close enough, or you went just over like 0.01 or 0.02, you know, that's okay. So in a case where you're kind of too far to technically round, you have to sort of find a number at which you needed to multiply that number by to get a whole number. So obviously if we took 2.5 times 1, that is 2.5. We took 2.5 times 2, that is going to give us 5. So the factor by which we would want to multiply that empirical formula is by 2, and it's not just a 2.5, but it's everybody in the formula. So we would want to take this guy and then multiply it by 2, which would give us A2, and I know the alphabet B5, yes. And that would be our proper empirical formula. So if you don't hit a whole number, and it's definitely not close to round, sometimes people ask how close to round, it pretty much needs to be the whole number, just underneath it or just above it. If it's any further than just like right at that whole number, above or below, you really should find a factor to multiply by to get the empirical formula. Any questions on any of those steps? So grams to moles, divide by the smallest number of moles. If you hit whole numbers, you're good. If not, you need to figure out how to get to a whole number. And that would be how you get to your empirical formula. Okay, so let's take a look at one together here as to how we would go through a problem like this. So let's see here, we've got one coming, I think. So we want to determine the empirical formula here for vitamin C. It was found to be 40.92% carbon, 4.5% hydrogen, and 54.5% oxygen. Again, you do want to kind of quickly take a look at the percentages and make sure that you are at 100%. You're not missing anything. Here we are about 100%. We could then assume 100 grams in this case, which will turn our percentages into the same numbers, but grams. And if we do that, that would give us 40.92 grams of carbon. That would give us 4.58 grams of hydrogen. And that would give us 54.5 grams of oxygen. Again, here, we just want to convert them into grams and keep the numbers the same. So we assume 100. At this point, the next thing we want to do is take each of these grams and convert them to moles. So we'll use the molar mass from the periodic table. So we'll do 40.92 grams of carbon. We're going to divide by 12.01 grams per mole, which is the molar mass of carbon. We'll do the same thing for our other guys here. So 4.58 grams of hydrogen. We'll divide by 1.008 grams per mole of hydrogen and 54.5 grams of oxygen. divided by 16 grams per mole of oxygen. So that gets us for carbon 40.92 divided by 12.01 gets us approximately 3.407 moles of carbon. For hydrogen, 4.58 divided by 1.008 gets us 4.544 moles of hydrogen. And lastly, 54.5 divided by 16 gets us about 3.406 moles of oxygen. Any questions so far? So we got them to grams. We converted our grams to moles. At this point, we want to divide by the smallest number of moles. In this case, it actually is carbon, fairly close, but pretty close. So we will divide everybody here by carbon, which is 3.406, 3.406, and 3.406 in this case. That is going to give us for carbon 1. That is going to give us for hydrogen 1.33. And that is going to give us for oxygen, obviously, 1. At this point, our empirical formula would be CH 1.33 and O. Is that a good empirical formula? Can I leave it like that? I cannot leave it like that because my hydrogen here obviously is not a whole number. So this is an example like we were talking about. When we divide by the smallest number of moles, we actually do. So we do need a sort of number that we can multiply it by to get to a whole number. So again, if you're not sure right off the bat, you could just do trial by error. Do 1.33 times 1 obviously is 1.33. 1.33 times 2, 2.66. 1.33 times 3 is 3.99, and that is close enough to 4 in this case. So we can multiply this entire thing by that factor of 3, and that should give us C3H4O3, which would be the correct empirical formula in this case. So in that case, as you can see, 3.99, close enough to 4. So you don't have to continue to hit a perfect whole number. And that's really based off of this division here. When we did this division, if we kept a whole bunch of numbers, the numbers like 1.3333, a whole bunch all the way down. So we could just round at that point. Any questions on the steps here to calculate an empirical formula? Okay. All right. So I feel good about it. I'm going to lay it up there, I think. All right.